Good afternoon. Hi, my name is Bonnie Shaw. I'm one of the 100W instructors here at San Jose State. And it is my honor to introduce to you my uncle. This GreenTalk speaker today is Bill Dunckel. He is an alumnus here from San Jose State University. He graduated with his master's in industrial and systems engineering back in the 70s. He has taught classes for industrial and systems engineering here at San Jose State and helped develop a couple classes here. And in the mid-'80s, he actually earned his certificate in professional engineer. What am I forgetting here? He has worked briefly through the San Jose State Foundation as a consultant for local manufacturing firms as well. And he has been a mentor for San Jose State summer interns. So please give him your full attention. Make sure that you stay until the end of the GreenTalk after the Q&A, and then do feel free to ask him questions after the GreenTalk, after he's done presenting, and then after the Q&A is over, do feel free to come up and converse with him individually. So with that, please join me in giving him a warm San Jose State 100W welcome.
Thanks, everybody. Appreciate being here. Yeah, I guess as Bonnie said, I am an alumni from the Industrial Systems Engineering Department. Since I got my professional engineering license in '86, about 20 years of that I've spent in the energy industry. So that's why I'm talking about engineering and environment and energy. I am representing only myself, by the way, so any past or present employers got nothing to do with this. That's my legal disclaimer. It's just me. My purpose here today is, I hope with whatever inspiration you hold right now, you're inspired to some extent because you're here taking time, getting an education, learning skills, that inspiration you'll be able to put in practice, and I hope to provide you some ideas of how to do that. All right, so what's engineering? Or for that matter, any other technical thing? Okay, the basis of economy is these first three things, which everybody does, is you see a need, and you identify an opportunity to meet that need, to either benefit society or create a business or something. And then you identify a solution, so you're offering solutions to meet the need. Okay, everybody does that. That's how business works. But in the technical world, particularly in engineering, what we need to do is predict and confirm the performance of that solution we recommend under all conditions. Now, for example, you have an air conditioning system. You want to make sure it works on the hottest day. You want to make sure it works when it's really wet outside or really dry outside or when it's actually really cold. You don't want to be freezing people. So that's an example of every condition you want to check for. And that occurs for software, for buildings, for hardware, pretty much anything technical. The other thing, too, if you want to step up to be a professional engineer or you just want to step up to be a responsible citizen, we are responsible for the safety and well-being of the public. And that means if you design a solution that satisfies your client but harms the public, that's not a good thing. You could make this air conditioning system that works, but it pollutes like crazy. Well, that'd be a horrible thing. So in everything we do, as I'll show later, we have responsibility to watch out for the benefit and safety and well-being of the public. Now, we have a problem with the environment, right? There it is. It's that globe and the atmosphere it contains, or that surrounds it. We get one of them. We don't get to replace it. No do-overs. So we have to take care of it. Now, when you think of the first law of thermodynamics, conservation of mass, that tells us that everything that comes out of our activities on the Earth stays on the Earth, including all the undesirable byproducts, heavy metals in the water, carbon dioxide in the air, and so forth. We design products, systems, and processes that all impact the Earth. Second law of thermodynamics. Entropy increases with every reaction. Entropy is unusable energy. Generally, when you're talking about pollution and entropy, it kind of goes together. wasted heat goes off in the environment. That impacts it. That changes the ecology of a local area, and so forth. So everything we do impacts the environment, generally in a negative way. And it's our job as engineers and techs to do something about this. But how? All right, here's an example of something I did way back. My job was to do the financial analysis and the engineering to recommend a replacement for a thing called a flat work ironer. That's an example of one. Basically, it heats, it has a bed that's hot, about 180 degrees, and you run sheets and towels through it and so forth. It irons it, it dries it, and they come out actually folded at the end. Now, there's two ways to do it. Either they have natural gas and a flame heating oil that creates the heat in the bed, or they put in high-pressure steam. In our case, we had an old one with high-pressure steam. So I did the analysis, and I figured out, well, I could go either way. It's not a big cost. We figured out the brand, we figured out the model, we figured out the attributes of the one we want. Then I talked to our chief engineer. And he said, you know what, let's think out of the box here. Don't just think about this machine. Let's think about the whole system and the impact. We are a hospital. We're interested in the health of people, and especially the air and our contribution to the air pollution in the neighborhood this hospital is located. So he said, all right, think of this. I've got a boiler room. I have 3 boilers in it. Those aren't actually his boilers, but that's about the size we were talking about. The third boiler has only one purpose, and that's to create 120 psi steam for that one flat work iron. So he said, if you can get rid of that flat work iron and use the natural gas oil heated one, I can get rid of that third boiler, completely get rid of it. Now I'm going to save all the pollution and the natural gas consumption of that third boiler. And also, these other 2 boilers, I can run them at a much more effective load, and they'll have less pollution also. So in the end, because that chief engineer thought in a bigger world, he thought about the environment, he thought about the impact of our selection of this one machine, he helped to save a lot of pollution that was going up because of these boilers. So that's a way of getting out of just thinking about the one thing you're going to do and think about the impact, all the various impacts that one choice could make. All right, well, you might say, why go to all this work? Let's just pick a clean source, right? I've got an electric car, right? Well, I don't really, but if I bought an electric car, yeah, I could say, look, I have a clean car. I'm not polluting. Ha-ha, I'm doing better than you. Yeah, well, really, wait. If we just restrict our talk today to clean being carbon emissions, right, because that's a sort of a level of a measure of trade these days. It's an international concern. Okay, some sources will pollute the environment less than others, but they all have undesirable byproducts. Now, as I'll show you later, why the electric car is not such a great solution. But one thing to remember is all sources have undesirable byproducts or impacts on the environment, but not one single source, even if we had a clean source, not one of them can meet all our needs. In fact, not any single source could even close to meeting the energy needs of the United States. For further information about this, you could consider Mechanical Engineering 172, Alternative Energy Sources, taught by Francois Ranger. And as a matter of fact, he gave me a couple of slides, which we'll see next. But it'll get in the thorough discussion of our energy situation and what our different options are to meet it. Oops, wrong button. Okay, here's one of those graphs. If you note, around about 1900, 1950, we start using a lot more energy. In fact, it kind of ramps up around the Civil War. We start losing coal. Think coal. Yes, coal's that black line. And even though this graph is kind of outdated, look at the top 3 here: petroleum, natural gas, and coal. The one thing those 3 things have in common is they are the most carbon-intense source of energy. You know, hydro, very little carbon in that, if any. Nuclear, biomass even. Those things don't really produce a lot of carbon dioxide or other carbon emissions into the air. But the 3 big ones that are most of our energy sources, they produce the most carbon. And you see that graph continues to go up. Now, here's another way of looking at that information. factor in around the Civil War, we had 288, let's just say 300 parts per million of carbon dioxide in the air. A little few years ago, measured, we're approaching 400 parts per million. So yeah, that seems like a lot of years, right? 150 years or so. But if you notice about the only thing that's happening here is this blue part, 73 parts per million, or is that 78? 73. The ocean is absorbing carbon dioxide, and of course trees are absorbing carbon dioxide, but also things are rotting in the forest, so the land sort of comes out even. But the point is, with an increase of 100 in 150 years, how long is it going to take for just that 73 to catch up? Well, it'll never catch up. If we stopped polluting today, it would take some 200-300 years for the Earth to clean up the carbon dioxide we spewed out since the Civil War. So we have a problem. We have to clean up the Earth, and the point of this slide is the Earth cannot clean up itself. We made the mess. We have to clean up after ourselves. Shoot. And they say everything you learned was in kindergarten. Well, there's one of them. Clean up after yourself. There we go. Now, there's another piece of energy equation here, which is the end use, right? Once you get energy where you want it, like the electricity got into the, got up here in the ceiling, we have to produce light from it. That's an end use. These aren't any magical categories. I just thought them up to sort of explain, put things in perspective. Heating and cooling. That's a big area. Commercial buildings, residential houses, even industrial processes, they consume lots of energy. Lighting. Our homes, our businesses, even the lights out in the street, all the signage, those Jumbotron units now that people are using for billboards, all that's consuming energy in terms of light. Mechanical motion. The big one here is transportation. And another form of transportation is water. We pump a lot of water up and down this state, right, to get it all the way down to Southern Cal. That takes massive, massive amounts, thousands and thousands of horsepower of pumps running pretty much all the time. Plus, our whole wastewater systems have a huge amount of filtering and other energy-intense things in order to return that water back into our water tables. Massive amount of energy. And then finally, that's what I'm hinting about with the electric car. Electricity generation is a big consumer of energy itself. Other than photovoltaic, electricity comes from generally heating up steam, running steam through a turbine, and the turbine turning a motor, and that motor creates electricity. And all of that has efficiency losses. So electricity is a great thing once you've created it, but it takes energy and pollution to create it. So the other thing I want to point down here is electronics, because I grew up in Silicon Valley. This place was mostly orchards when my family came in here, and I think they had developed, the semiconductor chip was just getting started. And since then, electronics have taken over this valley, and because of all the innovation we do here, electronics is taking over the world. When I was in college, the internet was teletype machines. You basically delivered text over twisted pair landlines, well, not local area networks, but in those days, like phone lines, and it would type out more stuff. That was it. It was like just sending text. That's all it did. Nowadays, it does everything. We are connected like the Borg. All that electronics, the thing about it is the energy increase is ramping up tremendously. It's not the biggest segment of energy right now, consumption, but it's ramping up tremendously, and we can do a lot about it because we make it here. Okay, visual. All those words kind of summarized down in here. On the left side, we've got the sources of energy. The boxes sort of represent the percentage of energy in the United States. And you notice the big ones are petroleum, this green thing, coal, gray, natural gas, blue. Now, that sort of mustard-colored thing up there, that's electricity generation. It's a big chunk. And what feeds electricity the most? Well, coal and natural gas. And remember, those are two of the three carbon-intense sources. So how clean is electricity? Yeah, not so good, necessarily. Petroleum, that pretty much goes into transportation. And all the other pieces, by the way, they are important because with all those pieces, all the different kinds, wind, solar, hydro, we can meet our energy needs. And the more we develop this technology, the more we can reduce these at a rate at which they can get cleaned. We won't be able to get rid of them. Remember something, for example, you're in Virginia, coal's almost in your backyard, that is what your power is going to come from. It'd be pretty hard to convince people to put photovoltaic systems in Virginia because you'd ruin their whole economy getting rid of coal. So these things will be around for quite a while. Technology has to learn to make them cleaner. Now over on the other side, over there we have a dark gray represents useful energy. It's about 40%. The one above it in the light gray is wasted energy, generally heat, and that's about 60%. Now, most of my background in the energy industry was in improving the efficiency of the end uses, which is changing the ratio over here. We have a 40 useful, 60 not useful. So what if we switch that ratio to 60-40? That means we get 1.5 times as much useful output, 1.5 times as light, 1.5 times as miles in our cars and so forth, per amount of energy consumed. If we can improve the efficiency, we don't have to change the quantity here, and we can get a lot more done. Imagine 1/2, again, 50% more just by changing efficiency, and we can do it. Part of the deal is the efficiency's out there, people just aren't using it. Okay, so basically, I'm try to sum this up in a sort of circle diagram. I'm a system engineer. Everything in my life is a system that goes in circles. So we have a lot of sources of energy, but none of them are perfectly clean, and not one of them will meet all our needs. We need to use all our sources. Number two, you can't just choose a source of energy because there's more things that impact the environment than just that source. You have to convert, transport, and capture that energy. Let's say you have raw crude oil in a 55-gallon drum. That doesn't do you any good. You could light it on fire, but it wouldn't do much. But it doesn't propel your car. You have to convert it into gasoline. So what? You have to build a production facility up in Richmond or something to convert that crude into gasoline. And that uses massive amount of seawater. It pulls out of the delta to cool it down. And manufacturing it has other byproducts. There's, oils and filters and all sorts of things. Plus, the environmental impact of all that steel to manufacture that refinery, and so forth. And then you have to transport it. You have to put it in pipes or trucks or something and run that down to San Jose so you can pump it out of the gas station into your car. So that's that capture, convert, and transport. It has a lot of impact. I just call those manufacturing byproducts, equipment manufacturing byproducts. Making the manufacturing system to get that energy to you hits the environment. Next thing is, which is kind of straightforward, is here. The end use, like I talked about, this is where the efficiency comes. If we can improve that, that's a great way to improve the whole cycle, but we will generally produce exhaust and heat, right? If you got an air conditioning system, it's producing excess heat. You have a car, it's producing exhaust. If you have a boiler, it produces both. So those are the byproducts we want to try to minimize. As we minimize those, we improve the efficiency of the end use, and we demand less energy for the same result. But that's what people generally think of. Okay, I got an electric car, it doesn't produce any exhaust. Well, actually, you know what? What happens to your tires? Rubber, does it just, it kind of basically evaporates. It doesn't really evaporate because it's not via moisture. It doesn't become anyway, it's not liquid, but it goes off in powder. And that powder actually goes up in the air, floats way up there and comes down miles away. And a lot of it you have breathed in tire dust, whether you know it or not. So there's impacts of everything. Finally, decommissioning. That means when my refinery is starting to fall apart because it's too old, or we have to change the formula so much that we have to replace this section with that section, that old, obsolete stuff has to be torn down, ground up, melted down, or whatever, and replaced with something new. That, of course, hits the environment. Secondly, how about your car? After a while, unless you've got some cherry muscle car from the 70s, you're going to probably just get rid of whatever you're driving today and replace it with something later on. What happens? That gets crushed, squashed, ground up, melted. In fact, somehow they managed to ship those clean over to Japan, then melt them down, make cars, and ship them back. I never understood how that economy works to haul all that stuff across the globe, but there's an impact on the environment, right? Getting rid of your car means somebody's going to have to drive a diesel truck over to a shipyard and put it on a big diesel ship and drag it across the ocean and so forth. So decommissioning is part of the game. Point is, if you want to decide what's clean, look at the whole cycle and realize that whatever end use you choose, you're kind of responsible for all the other pieces, right? Because you're impacting the environment indirectly with that. So measure the whole footprint when you're trying to recommend something. The other thing here is a little bit of detail. Here's an example. Somewhere between 1.3 and 6.7 million electric vehicle batteries will be obsolete and ready for disposal around 2035. Right now, to my knowledge, don't really recycle those. Nickel metal hydride is sort of recyclable, but not completely, and it's a big impact to do it. You can do it, but it impacts the environment again. If we move to lithium, we're going to be a lot better off. But a lithium-ion battery of 300 pounds, pretty expensive proposition. So technology, again, can get us there. There are many, many battery options. There's one of them called aluminum air. It's in the R&D stage. I actually got to use one once. Put a sheet of almost pure, well, 98% pure aluminum into basically a water container, and you produce electricity. You've got little controls and electronics in there to make it work. But it basically dissolves aluminum, leaves aluminum nitrate, and you can easily clean that up. So that's a fairly low impact technology. So anyway, everything has an impact. You have to look at the entire circle to decide which solution you are recommending has the best impact on the environment. Okay, so what was the solution so far? Way back in the 70s, Jimmy Carter was president, and we had oil embargoes. So we didn't have enough crude oil to go around to power the United States. And so we came up with the notion of conservation. That was a great thing. The politicians could get behind. Everybody can be patriotic. I said, okay, I'm going to do my part in helping the United States not be, at the mercy of the oil-producing nations. And we're going to get through this energy crisis together. So I'm going to get rid of my big car, and I'm going to get a nifty little Honda like this that gets, well, back then, 28 miles a gallon was astounding. And that's how we're going to do it. Now, conservation means pretty much don't waste what you're not using. Simple example, which I'm trying to get through to my family, is where you're not in that room, turn the light off. Right? Why have the lights on in the hall of the house? Why are the lights on in the kitchen, in the bedroom, in the laundry room when you're sitting in the living room, watching TV? Turn them off. If you're sitting there with your shorts and your T-shirts and your flip-flops and you're feeling cold, don't crank up the thermostat to 70. Put a sweater on. Put some socks on. That's conservation. There's nothing wrong with it. Trouble is, it's hard to sustain. It's a cultural shift. It's a behavior. It's kind of a popular thing. I mean, for example, we're talking about carbon, reducing carbon, global warming. If people stop talking about this, I'll tell you, in 30 years, people won't be paying attention to this anymore. Point here, took a picture of this little guy here in a Costco parking lot. Now, thing you can't see, there's not